Problem 138 from Chapter 16. Collar B moves to the left with a speed of 5 meters per second, which is increasing at a constant rate of 1.5 meters per second squared relative to the hoop, while the hoop rotates with an angular velocity and angular acceleration shown. That's here. Determine the magnitudes of the velocity and acceleration of the collar at this instant. So first we want to take what they gave us in this problem and write it down. So the angular velocity and angular acceleration of the hoop. I'm going to use that for the angular velocity and the acceleration of my rotating coordinate system. So my rotating coordinate system is rotating with the hoop. And let's do this and say, for my rotating coordinate system, this is the x direction, and this is the y direction. That's rotating with the hoop, so sometime later, x is going to be down here. And I have angular velocity of the coordinate system is 6 radians per second. And it's rotating this way. So that would be the negative k hat direction. Angular acceleration of my coordinate system is also in the negative k hat direction, and that is the 3 radians per second squared that they gave me. Okay, and then with a speed of 5 meters per second, which is increasing at a constant rate of 1.5 meters per second squared, that's velocity and acceleration. This is relative to the hoop. Relative to the hoop means that it's measured by someone who is in the reference frame of the hoop. So that would be the velocity of B with respect to, let's say, point A. That's here. That will be the origin of our rotating coordinate system, as shown there. X, Y, Z. Now moving to the left, that would be in the negative I hat direction. So this is 5 meters per second from the coordinate system I have here. That's in the negative I hat direction. And the acceleration is in the same direction. The acceleration of B as measured by someone at point A and rotating with the rotating coordinate system is negative 1.5 meters per second squared, J hat. I think that's everything that I need. Okay, so we're going to use equation 1626 to find the velocity. So I have equation 1626 here. The velocity of point A is 0 because point A is not moving. It's staying in the same spot. Okay, angular velocity is negative 6 radians per second in the k hat direction crossed with my position vector. I didn't figure out what my position vector is yet, but this is point A, this is point B. That distance is 0.45 meters. So the distance from point A to point B is 0.45 meters. Pointing from point A to point B is going in the negative j hat direction. Plus the relative velocity, that's relative velocity is here, negative 5 meters per second. I hat. When I do the cross product here, k hat crossed with j hat, k hat crossed with j hat gives me negative I hat. I have a negative sign here and a negative sign here, so it's still negative I hat. And 6 times 0.45 gives me 2.7. So this is 2.7 radians per second times meters is meters per second. And both these components are in the I hat direction, so that is negative 7.7 meters per second in the I hat direction, but they asked me for the magnitude. And so the magnitude of the velocity is just 7.7. So this is 7.7 meters per second, and that is our answer for the velocity, the magnitude of the velocity. Now we want to find the magnitude of the acceleration. So this very long equation, which doesn't all fit on the screen at the same time, is equation 1629. Thankfully, many of these terms are equal to 0. So point A here has an acceleration of 0. It's not going anywhere. Point A is staying in the same spot. The hoop is rotating, but point A is not translating. We actually do have angular acceleration for our rotating reference frame. So we're going to use that here. So this term is non-zero, this term is non-zero, this term is non-zero, and this term is not zero. So we have four different things, four different terms here, and we have cross products for three of those different terms. So let's do the cross products first before we plug everything in. Okay, so I have angular acceleration for my rotating coordinate system is -3 radians per second squared in the k hat direction crossed with my position vector, which was -0.45 meters in the j hat direction. And doing that, the 3 times 0.45 gives me 1.35. And radians per second squared times meters gives me meters per second squared. And I have a negative sign here and a negative sign here, so that gives me something positive. But I do k hat crossed with j hat, and that gives me negative I hat. Okay, so that was our first cross product. Now, our second cross product here Okay, so I had some technical difficulties there. I went to get rid of the sunlight shining on the paper here, and I never started recording again. So we're going to go back to the second cross product here, and we have for the angular velocity -6 radians per second in the k hat direction crossed with angular velocity crossed with a position vector, but we did that cross product up here. That was this, which gave us -2.7 meters per second in the I hat direction. Okay, so this is what we have in parentheses here. And when we do negative and negative, we get a positive something in radians per second times meters per second would be in meters per second squared. And k hat crossed with I hat gives me j hat. And finally, 6 times 2.7 gives me 16.2. Okay, and then moving on to the third cross product, I have 2 times omega. Omega is -6 radians per second, so this is -12 radians per second in the k hat direction. So 2 times omega crossed with my relative velocity. My relative velocity is -5 meters per second in the I hat direction. So -12 times -5 gives me 60. Radians per second times meters per second gives me meters per second squared, and k hat crossed with I hat gives me j hat. Okay, so now I have my 3 different terms from the cross products taken care of. And then I have to add the relative acceleration here. Now let's go back to what they told me in the problem. So here I had the collar moves to the left with a speed of 5 meters per second, which is increasing at a constant rate. So the speed is increasing at a constant rate, but the collar, now even if you are standing at point A, you're going to see the collar moving in a circle. Okay, so you are rotating with the hoop. So if you're standing at point A, point A moving or rotating with the hoop. You don't see the hoop rotating, but B is still moving in a circle around the hoop. So B is moving in a circle, even for an observer, rotating with the rotating coordinate system, and it's the speed which is increasing at a constant rate. So if the speed's increasing at a constant rate, that's related to the tangential acceleration. So that's how the speed is changing. And let's go back to our equation sheet here. So the speed is changing. That's the tangential component of the acceleration. We also have a normal component of the acceleration. And because if you're standing at point A, you see collar B moving in a circle, you have to calculate the normal component of that acceleration. So what I did up here was not correct for two different reasons. First of all, I called this J hat, but that was how the speed is changing. That's in this direction. That was supposed to be an I hat. I don't know what I said there, but so that was supposed to be in the same direction as the velocity. Okay, so that's how the speed is changing. So this is the tangential component. I also have a normal component because for an observer at point A, collar B is moving in a circle. As long as an object is moving in a circle, if it's moving and it's going in a circle, it has to have a normal component of acceleration as well, pointed in towards the center of the circle. Pointed in towards the center of the circle would be in this direction, which is the positive J hat direction. So I have a normal component also. And that would be V squared over rho, which is the radius of curvature. That's the same as the radius of the circle that the collar is moving in is 200 millimeters. So this is V squared. Let's go back to our equation sheet. V squared over rho. The speed of the collar is 5, so that's 5 meters per second squared divided by the radius of 0.2 meters. So divided by 0.2 meters, and this is in the J hat direction because when the collar's here, pointed towards the center of the circle is J hat. Okay, so now that we have that taken care of, we can go back to our equation here, and we're going to put this in for the relative acceleration, and now we can put everything together and find the acceleration of B. Okay, so this first term is 0. The second term is negative 1.35. You know, everything's in meters per second squared. This is 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 meters per second squared. And if I do meters squared over second squared divided by meters, that's in meters per second squared also. So let's put the units at the end. And this is 1.35, negative 1.35 in the I hat direction. That's for this term here. For the second term here, that's plus 16.2 J hat. This third term here is 60 J hat. Then I have to do plus the relative acceleration, which is negative 1.5 in the I hat direction. So minus 1.5 I hat plus 5 squared divided by 0.2. So that's 25 divided by 0.2. And that gives me 125. So this is plus 125 J hat, and all of this is in units of meters per second squared. So now I can add all the I hat terms together, and I can add all the J hat terms together, and then I should be good. Okay, so I have 125 plus 60, that's 185, plus 16.2, so 185 plus 16.2 gives me 201.2 in the J hat direction. In the I hat direction, I have minus 1.35, minus 1.5, that's minus 2.85. In the I hat direction, so that is the acceleration of b. But that's not what they asked me to find. They asked me to find the magnitude of the acceleration. So to find the magnitude of the acceleration, I use the Pythagorean theorem. I square the I hat component. I square the j hat component. Add them together and take the square root. And for that, I get, with 4 significant figures, it's 201.22. I mean 0.2, but it's not exactly 201.2 because that's what we had just for the y component. So it's 201.2 meters per second squared. So let's just say now 201.2 meters per second squared, and that is the magnitude of the acceleration. Okay, so that concludes problem 138 from chapter 16.